Chapter 6 is talking about how do we deal with the imbalanced problem on the grade prediction of the y. By looking into the thesis of the chapter 6, I try to rearrange a little bit about how does it present according to the way I think is easier to understand about the presentation. So what I do is that starting with the problem statement, try to understand why do we have this problem and how do we evaluate our results. After that, we looked into different methods and talk about the results directly together with the method description, because there are several methods has been introduced in the chapter, at least 7 of them, and I picked several important of those methods and to discuss about what is it try to do and what's the comparison results. And finally, we try to draw some conclusions about this chapter. So starting with the problem definition, by looking into the data set for the y, we try to category those y grades according to its grade. So starting with the leftmost, these are the y's with grade between 80 to 84. This large chunk of the y's falling into this category, which is between 85 to 89. The next one is actually one of our targets in this chapter. This is about the outstanding y's that score from 90 to 94 and classic. You can see the y being categorized as classic, which receive y score that are 95 and plus, is much smaller compared with the outstanding y's. Therefore, in our previous chapter, we try to make some predictions saying that if we have the y that receive the score above 90, and we try to look into all of those y, class 3 and class 4, building a SVM classifier, we are able to make the predictions with 95% and above accuracy to predict whether this y belongs to categories 3, which is outstanding, or class 4, that is considered as classic, which receive 95 plus about a y. And of course, that is actually a very glory indications that those y's are considered as classic. Although the prediction accuracy is as high as 95%, it is actually misleading. Why is that? Because the data set is highly imbalanced. It is about 1 to 20. The 95 plus y's consist of less than 5% of the data set. So what this classifier trying to do is that it simply predict everything into outstanding. There is no y being predicted as class 4 that are 95 plus points wise. And therefore, because of the data distribution wise, we get the accuracy of 95%. And that's simply because we predict everything into the class 3 outstanding y's. And therefore, accuracy in this scenario cannot help us understanding the performance of the results. And that's why we need to rely on something else. And therefore, the two most important evaluation metrics used in this chapter are precision and recall. So what is a precision? Precision is indicating the true positive divided by true positive plus false positive. So what they're trying to do is that true positive plus false positive indicating all the y's that you predict it as positive. And of course, if we consider 95 plus 1, which is category 4, as positive, that's going to be indicating that how many corrected predict 95 plus y's divided by all predicted as 95 plus 1. So in other words, if the SVM try to predict this y as 95 plus, what is the accuracy? What is the precision? Well, how possible that y is going to be considered as 95%? For example, if precision equal to 50%, that is to say there are 50% of the opportunity that this y belongs to 95 plus is if it is predicted as 95 plus. That's what they try to represent. And you need to understand that it is very hard because there's only 5% of the y that are considered as 95 plus. So in other words, if you leave to opportunity, you can get 5% if you flip a coin, basically. The recall is slightly different. It's still true positive divided by true positive plus false negative. True positive indicating that if you predict it as positive, which says 95 plus, then that is a true 95 plus y. For false negative, what it's trying to do is that it predicted as negative, but it's false. In other words, you predicted wrong. Therefore, what this recall trying to do is that correctly predict 95 plus y's divided by all of the 95 plus y, which means the 5% of the data set that we have over here. So among all of those 95 y's, how many of them can be correctly predicted? And therefore, precision and recall are the two most important evaluation metrics that we want to use in this chapter. So what we try to do is we use a 5-fold cross validation, and then we train by SVM as our classifier. Since SVM has many different kernels that are available, we try all 5 kernels out of those and then try to report the best performances that we have. And that is how we set up the experiment. For the methods and results, methods, I have categorized those methods into 3 categories. The first area is undersampling versus oversampling, and then we want to talk about clustering-based methods, and finally, we looked into more sophisticated way of doing the imbalanced data set. That's what we call the SMOT, as well as the borderline SMOT. For undersampling, what we try to do is that since we have an imbalanced data set, undersampling is trying to look into the majority of the y, basically is between 90 to 94, and we try to randomly select some of those. Out of all the data set, we try to select the same amount of y's with the 95 plus y, and we do the training. So that idea is very simple. We randomly pick some of the majority class. So we try to sample outstanding y's, and then the idea behind is this: by removing many of the majority class instances, the data can be balanced without needing to create or collect any more data. And the positive part about this one is that besides it's super simple, it is also trained a much smaller data set in this case. But of course, we may end up with information loss over here. The opposite side of undersampling is oversampling. So instead of reducing the size of the majority class, we can increase the size of the minority class. In other words, we try to oversample of classic y's. If we randomly take instances of minority class and repeat them, so the oversample is also very simple. We look into minorities and then we try to replicate those y's to make it a certain degree of the percentage compared with the majority. And in this case, we can have a less unbalanced situation. In this case, it is, of course, computationally inefficient. We are actually creating more data when we try to train the SVM or classifier. It may take more time to generate the model that we have. So look into these 2 simple methods and we try to take a look of the performance. So if we do undersampling, which means that we try to undersample the majority of the y, and then what we would get is that we have the precision that close to 20%, and the recall, it goes to 31%, which means that if the y is predicted as classic, which is 95 plus y's, there's about 20% of them that are true. It may look low, but compared with flip a coin, you get 5%. It's actually a big improvement. Compared with our original results, since all of the predictions are majority, then there is actually no wines being predicted as 95 plus. And you can see this is actually an improvement out of that. Additionally, of all the minority instances, with the 5% of the classic wines, we actually can predict 31.7% out of those, compared with previously 0%, because none of the wine is being considered as classic. So you can see that this is something that we try to improve. You need to understand one thing: by increasing the precision and recall, the cost is that we actually reducing the accuracy. But that is some trade-offs that we need to do in terms of the imbalanced data set. On the other side, for oversampling, we try to replicate the minority of the wines, and we actually get with pretty good precision, 26.6% compared with 20% is actually a big improvement. At the same time, reduce the recall a little bit to 31.2%. So in this case, comparing undersampling and oversampling is actually doing a pretty good job. Now, we use wine as the example because it's easier to look into the situation. The same scenario can be applied in everything else, such as the credit fraud situation or some outlier detection situation. You can see that for the credit fraud, there's actually a very much lower percentages compared with the regular transactions. However, you can see in this case, we can increase those precision and recall while we may reduce the accuracy slightly. But if we can cut 31.2% of the fraud, it's actually not a bad situation. We will be able to raise the alerts in a better scenarios other than not predicting anything. So the other method is what we call clustering based. So in this case, we try to cluster the data sets that we have. In other words, we try to cluster the majority of the wine, which are wine between 90 and 94 scores, and then within the class of outstanding wines, it is possible to subdivide them even further into groups via clustering. So each cluster represents some test profile in the outstanding wine category. And we don't want to discuss all of the instances within a cluster because each cluster represents something. And therefore, what we try to do is that we go into each cluster and then select the data to keep, then it is to remove. In other words, we find the points that are close to the center of the cluster that we add it into the instances that we want to keep those wines. And we can repeat that process, go into each clusters that we generated. Say that in the first round, say we have 200 clusters. We try to pick the center of the cluster as our first round. So we collect 200 majority wines, and then we can repeat that every time we do that once. We collect additional 200 wines, and by doing so, we can more actually selectively find the wines that we want to include into the majority. And still, it is the idea of undersample of the majority by adding the wines that we think they are representative. So what we have done in the experiments is that in representative clustering, we vary the number of the clusters from 10 to 90 with a size of 20. So we're starting with 10 clusters, then go to 30, go to 50, go to 70, go to 90. And after that, we tried 100, 200, 300, 400, 500, 600, and 700. So we tried many different number of the clusters, and at the same time, we also try to include, after the cluster are generated, we go into each cluster, try to collect the wines that we are interested in. First of all, we collect the same size with the minority, and we collect, next round, we collect 2 times of the size of minority. 4 times, 8 times, and 60 times of a minority. And we try to see, once we feed those data sets into the SVM, what do we get for the results? So these are some selective results that we want to present here, starting with the 95 plus great representative clustering, and we use the equal size classes. So when we come to the equal size of the classes, indicating we select the same amount of ones with majority and minority, you can see that for 95 plus 1's prediction goes down, the 95 minus 1 goes up. And that is comparing with the number of the clusters. So if we take a look of this interesting one, when we generate 200 clusters, we are actually able to predict 1,400 ones that are 95 plus. Compare with the 95 minus ones, we actually can predict about 17,000 ones that are between 95 minus ones. So this is like the trading off point. After that point, we keep reducing the number of 95 plus ones prediction correctly goes down, the other one goes up. So that is what we have discovered over here. And therefore, depending on what is your emphasis, if you really want to find those outstanding ones, this is actually a good point. And of course, if you don't care about those mistakes, this is actually be able to give you the best results out of the 95 plus ones. When it comes to 4 times larger than 95 plus, so that means we have much more, 4 times more 95 minus ones compared with 95 plus ones. The similar results are generated. The only difference is that the cluster number goes to 600, and then we can still predict about 1,200 ones that are 95 plus, while compared at the same time, we can get much higher 95 minus ones correctly. So this is like, again, the trade-off between the clustering based. So finally, we come to a more sophisticated way of generating undersampling methods or oversampling methods. This is what we call SMOT. So SMOT, what is it try to do? SMOT is synthetic minority oversampling technique. It's a method to do oversampling on the minority class, which means that it goes to 95 plus ones and then try to create more synthetic 95 plus ones. But this time, it's not as simple as oversampling by duplicating the ones. What it tried to do is that it used the idea of the k-nearest neighbor concept. So what it will do is that instead of repeating the minority class, it generates new instances. And how do we generate new instances? We use the idea of the k-nearest neighbor. That sounds interesting, right? It's a combination of oversampling and k-nearest neighbor. So what it tried to do is that between every minority instance and its k-nearest neighbors, say 3. So what it will do is that for every minority, it will try to find 3 closest neighbors. And then it creates new synthetic data between the point you are looking at and with each of its k-nearest neighbor. And when it finds it, say that the k-nearest neighbor number 1, there is a distance between the target's minority data and its first closest neighbor. What it tried to do is that by using the distance between the two, it randomly generates synthetic data in between the two values, and it creates a new instance. And say that if our k-nearest neighbor, k equal to 3, it will generate 3 new synthetic data with its neighbors using random map value. So what it tried to do is like this, saying that this is our minority data set, and it tried to find 3 k-nearest neighbors. So once it identifies those neighbors, what it will do is that it will generate a synthetic data in between these two distances. It can possibly be very close or a duplicate of the neighbor, or in other ways, it can possibly be a duplication of the node itself. But usually, because it's a random value, you generate something in between. And therefore, when k equal to 3, you will be able to generate 3 new synthetic data. And they are not a simply duplication of the data. It is creating something that possibly being generated if we collect more wines, and that is something between the 2 points. So this is what we look into the smoke. On the other side, an even more sophisticated way is what we call a borderline smoke. So smoke can be extended to focus only on data that defines the border between the majority and minority class. This is super ideal for SVM because SVM is trying to use the borderline and to create a maximum hyperplane between the two classes. So this borderline small is a very useful way, especially if your classifier is SVM. So what it tried to do is that it still uses k-nearest neighbor on the minority classes like before. So the first step is the same. The second step is then different. It then calculates the metric to identify if a particular instance is on a border or not. Here is a very big difference between small and borderline small. For small, it tries to find the neighbors on all of its minority data set. So they only focus on minority data set. In borderline small, this is slightly different. You try to find the neighbors. It can be majority, it can be minority as well. So it looks for the neighbors on all of the instances. That's the difference between borderline small and small. Again, for small, it only looks the neighbors in minority. For borderline small, it looks neighbors for all of the data set. So now here's the 3 if statements in scenarios. If all of the instances neighbors are from majority, that means this minority is embedded in a lot of majority, then this is something that can be considered as noise. So we don't want to do anything about this point. If all of the instance neighbors are of the minority class, that means it is surrounded by a lot of minorities, then its instance is not on the border, so it is also skipped. So what we are interested in is that if the number of majority neighbors is larger than the number of minority neighbors, this instance is considered to be in danger. And those in danger points are the points that we want to focus on. And therefore, what we want to do is that for each instance is considered in danger, that's the only thing that we want to do things, then we go into m nearest neighbor between that instance and the other in danger instances is calculated. So it was using the same idea, generating the new synthetic data among danger points. So the danger points will try to look into other danger points and then try to create the synthetic data between those things. And of course, they're still using the nearest neighbor concepts over here. So synthetic instances are then created between the instance and the random sample of its m nearest neighbors, and those neighbors are also in danger neighbors. In this way, border between the classes is strengthened. So that it will be easier for the classifier to recognize the difference. And of course, the method is ideal for SVM because this is exactly following the concept of the SVM. Let's take a look at the example so you can see that the majority are the black dots, the minorities are the red crosses over here. And therefore, if we try to look into the in danger concepts, only those nodes that in blue are considered as in danger points, because you can see these red points over here are surrounded by the positive cases, which are considered as the minority. And if you have some red cross over here, that's indicating it's a noise over there. So we identify the neighbors, the borders, which indicating those are the points that are in danger. And then what we're trying to do is that we generate the synthetic data only among those in danger points. And that is what we call a borderline small, so it can reinforce the border of the minority class. And therefore, if we take a look at the results, starting with the SMOT, the number of nearest neighbor was varied from 3 to 9 with a step size of 2. So we try to look into 3 neighbors, 5 neighbors, 7 neighbors, and 9 neighbors. All of them perform very similar. So it's between 1,060 to 1,070 minority instances were correctly classified in between those 85,000 majority instances were correctly classified. And therefore, if we look into the precision and the recall, you will notice that the precision is actually lower than what we look into the oversampling and undersampling. But the recall is much better. In other words, we can identify way more 95 class wines among all of the 95 class wines. For the borderline SMOT requires 2 parameters because first of all, it needs to look into the k-nearest neighbors to determine the border. So it needs to identify the borders, understand what are the nodes are in danger first. And then for those in danger points, we also need another parameter nearest on the border neighbors to generate synthetic examples between. And that's why borderline SMOT has 2 parameters. In other words, this parameter was searched, although not exhaustively, with the value ranging from 3 to 23. And what we found is that if we have a combination of 3 and 21, this is one of the better results that we received. We have a better precision compared with SMOT, with slightly lower in the recall, but this SMOT seems are able to get the higher precision with lower recall compared with the SMOT. So these are the results that we have discovered, and of course we try much more different combinations of these to generate to pick up some results that we try to report over here. So here is the conclusion. These results are improved from previous research. While we identify the imbalanced situation, we found out all the wines are predicted as 95 minus 1. And we want to do something about it. That's why we spend some time to dig into this one and then try to see how can we work with the imbalanced data set. And I also feel this is a very important topic to be looked into compared with the real world scenario. So I want you guys to think about this. What does it look like? What kind of problems can be applied for this kind of imbalanced situation? So the cost is overall accuracy is decreased if we want to increase the precision and recall, as we have seen in this topic. Dimension selection, there's many different ways can possibly improve the results over here. One thing is dimension selection might be useful in this topic. More advanced natural language processings might be needed, so that if we can grouping those attributes into a higher level of understanding in languages, we may be able to get even better results. I want you guys to understand something. This chapter in the thesis is actually not generating outstanding result compared with all other chapters. However, in the thesis, sometimes you want to report things that you have done, even though they are not generating like excellent results. Because when you try to report something it works, as well as you report something it does not work, they have their scientific values already. It is, of course, totally possible to keep digging into this part. At the time, we just feel some other topics in chapter 7 as well as chapter 8 are more interesting than this one. So we did not keep digging into this area. However, like we mentioned, imbalanced data set scenarios is always an interesting topic to work with. And that concludes the chapter discussions about this chapter 6 imbalanced scenario.